So I'd like to go ahead with complex reasoning, and we've talked a little bit about reasoning and language models up until now, and so I'm going to be talking about stuff that we didn't talk about yet. This might be a little bit short because of that, because I'm not talking about like programs, because we talked about that in the code generation class, and we already talked a little bit about some of the basics here. But if we have time at the end, I'd be happy to discuss freeform also. So what is reasoning? The basic idea is using evidence and logic to arrive at conclusions and make judgments. And what is it in language models is a little bit, less clear. But if we talk about it kind of like from the philosophical standpoint, there are two varieties of this. One is formal reasoning, and formal reasoning is mostly based on strict truth values. So it's kind of like you can definitely say this is true, you can definitely say this is not true. And in real life, there's very little actual formal reasoning outside of, like, for example, mathematics, or maybe, algorithms, computer science, and other things like that. And then separately from that, we have informal reasoning based on experience and intuition. And actually, this was rather elusive until large language models. People were working on it, but it was really hard. And this is like one of the big breakthroughs, I think, of the past few years. I should note that this paper here, Huang and Chen, is a kind of review survey paper of reasoning in large language models. It's on the references, so if you're interested, you can take a look at that too. But there's three kinds of reasoning. There's many kinds of reasoning, but there's three kinds of reasoning in particular that I'd like to talk about from the point of view of today. And the first one is deductive reasoning. And deductive reasoning is basically using logic to go from a premise to a conclusion. And this is largely what people, not entirely, but largely what people talk about when they think about formal reasoning. And so basically, you have several premises, like all mammals have kidneys and all whales are mammals. And then from this, you can go to all whales have kidneys. Then separately, there's inductive reasoning. And inductive reasoning is from observation, predict a likely conclusion or predict a likely kind of generalized conclusion. So this is one example. When we see a creature with wings, it is usually a bird. We see a creature with wings, the creature is likely to be a bird. So this is kind of like a soft version of deduction. Another common thing is like, every single creature I have seen with wings is a bird. And then you can kind of induce that all creatures with wings are birds. But that might not be true. It's not necessarily logically entailed, but you make that kind of logical conclusion without it being formally correct or verifiable. And then the final one is abductive reasoning. And so this is from an observation. We predict the most likely explanation. And so, for example, if we have something like the car cannot start and there is a puddle of liquid under the engine, then we might have a likely explanation that the car has a leak in the radiator. So we're going from kind of the car, these things, and then we try to predict the reason why this happens. So we're trying to predict like reverse causal links, essentially. There's other types of reasoning that I'm not going to talk about as much, like analogical reasoning and things like this, but these are the three main ones I want to talk about today. One thing I should point out is, like, even in philosophy, or, like, even when you read descriptions about these various types of reasoning, the types are a little bit vague. So take these as like general, not, general directions and not strict rules, because like which falls under which category also can be a little bit, unclear according to various definitions. Cool. So first, before getting into formal reasoning methods, or before getting into the bulk of the talk, which is going to be about LLMs, I want to talk about some pre-LLM reasoning methods. And the first one is kind of like formal reasoning within computational semantics. And this has been around for a really long time. It's also kind of what powered the things that worked over knowledge bases and other things like this. And the way it works is it does derivational reasoning by, sorry, I can't read that in the back. By starting out with certain premises and getting to final conclusions. So there's ways that you can write this. I think you might have seen this in another like math class or something, but we have symbols like all and exist. Let's see. Yeah, we have things like all and exist. And like all X die means like everything has died. And this implies that Mia and Zed have died. So yeah, this is actually maybe I'll not go through this one, and let me go through go to this one. So like it would be something like for all X mammal X implies have X kidney or something like that. And then you would have other rules, and you can go through derivations and other things like this. My favorite reference for this is this Blackburn and Boz book right here. It's really well written, and it has like lots of good examples. It also explains how you go through derivations and other stuff like that. And actually, neural networks can do this variety of reasoning through chain of thought and other things I'm going to talk about today, but it's a very rough approximation, and it doesn't work particularly well for saying like all people are of a like things that apply to all people or things that apply to sets or other things like this. So within Prolog, you could take a knowledge base and ask the knowledge base, like, do all people who work at CMU as professors have a PhD? And you could like actually examine that based on the knowledge base. Whereas even if you had a language model that had access to everybody's CVs, it wouldn't necessarily be able to answer that question. And it especially wouldn't be able to answer that question if you were wouldn't be able to answer that question if there were like multiple steps. So did all people who are working at CMU get their PhD after 1990 or something like that? So, and the answer to that is obviously no, but this would be able to find the counter evidence to that, whereas LLMs would not be guaranteed to be able to do that. So I think this is really like a nice thing to know, but there's a couple problems with it. The first thing is this really only traffics in like strictly true or strictly false statements. And that's a really big issue. So like if anything's soft, you start this sort of formal reasoning starts breaking down. The second thing, which actually is a really big problem, is once you start dealing with more complex things, you don't realize it, but there's always like exceptions and exceptions to exceptions and other things like that. And actually it becomes very computationally expensive to prove anything that's kind of like non-trivial. And so because of that, I'm not actually going to cover it in the lecture today, but recently there are kind of search algorithms through proof spaces that use like neural models to to speed up the search by picking the best and most promising hypotheses. And for example, Sean Welleck here at CMU is working on that for neural theorem proving, where you have like mathematical theorem proving, and then you use a neural network to pick the best paths through logical operations. So that's kind of a combination of the more classical and modern methods. Then another thing that's useful to talk about, I think this isn't very popular right now, but I think it might become more popular in the future as we start hitting the limits of what we can fit into long context windows for neural models and stuff like this, is memory networks. And basically, the way that memory networks work is they have the ability to write and read from memory. And so this figure is a little bit complex here, but basically you have a query, and then you get the embedding of the query. You take the inner product, you get the softmax of the inner product. So this looks like attention. You look up embeddings, and you take the weighted sum of the embeddings, and you get the summary of the memory. So this is basically attention over a big memory base. But then memory networks also have the ability to go in and update the memory. So they also have write operations. So you can read and write from the memory base. And so the reason why I say this might become more popular is one of the big issues with large language models nowadays is they don't get to continually update their memory. And one way you can do that is you can just add text to the memory, but there are certain limits to that, right? Text isn't necessarily the best way to encode all of the things that you've seen in the past. So I feel like this kind of architecture might be, how to pin these sorts of architectures onto language models might be an interesting research direction for the future. Another thing which I am not going to talk about very much, but because we kind of already talked about it in the code generation area, but it's actually been around for a while, is solving questions with sort of symbolic reasoning. And the way it works is, for example, you would have a text here. And based on the text, you can run these sort of symbolic operations like find and filter and find the max number and relocate and other things like this. And this explicitly manipulates kind of the attention and the, you can do things like filtering down to find the most largest number, for example, or other things like this. And this is kind of interesting because some of the things that neural networks are bad at are finding the largest number in a big data set, or finding all of the things where something applies and throwing out all of the things where something doesn't apply. So again, this isn't used super widely in large language models right now because I feel like people have been focusing on prompting techniques in order to do this sort of reasoning. But I think this is another thing that's worth thinking about, taking another look at and seeing if there are ways to incorporate it with the current models. Because basically what I wanted to say is all of the things that I decided to introduce here in this section are things that current models are still not particularly good at, taking many steps over sets of inputs, reading and writing from memory so that you can remember things over long periods, and also filtering down large pieces of text into smaller pieces of text to find relevant information. So if any of those things sound interesting, you can take a look at this. But after this, I'd like to go kind of into the main event where I talk about the stuff that people are actually using a lot nowadays. Any questions about these three? Okay, cool. So now I'd like to go into chain of thought and variance. And I actually have already talked about chain of thought. In fact, we've mentioned it a couple times, but just, to remind everybody, the basic idea is compared to standard prompting where we have a question and an answer. in chain of thought, we have a question, and then we have a derivation for the question. So like Roger started with 5 balls, 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 equals 11. The answer is 11. So you add this to the prompt, and by adding this to the prompt, you get the model to also do these derivations at test time. And this greatly improves some tasks. It improves tasks where we can't like immediately predict the answer directly. And then I also previously talked about zero-shot chain of thought reasoning, where we just prompt the model with something like, let's think step by step. And then the model becomes able to do this chain of thought reasoning. Okay, so that was review. And now I'd like to talk about some of like more advanced methods that people use for reasoning as well. And this is by no means an exhaustive list. They're just some of the ones that I found interesting. So if you know other ones that you'd like to talk about or introduce to the class or something like that, I'd also be happy to hear which ones you like or have heard about. But the first one is self-ask. And one of the issues with large language models nowadays is that they're not very good at asking follow-up questions, or maybe not that they're not very good at it, but just they're not trained to do it. So like if you play around with ChatGPT, I have never had ChatGPT ask me a follow-up question. I don't think it's like, it's not because large language models aren't capable of doing it. It's just that they like, OpenAI must think it's a bad user experience to have a language model that asks you follow-up questions. That's only like, reason I can think about it. But basically what self-ask does is it explicitly prompts the model to ask if there are follow-up questions. So here's an example on the left where the question is, who lived longer, Theodore Haker or Harry von Watkins? And basically it says, are follow-up questions needed here? Yes. And then the follow-up is, how old was Theodore Hacker when he died? And the intermediate answer is Theodore Hacker was 65 years old. How old was Harry von Watkins? Harry von Watkins was 69 years old. So the final answer is Harry von Watkins. And in this particular paper, this is just like another variety of chain of thought. It's like not using it to incorporate any external information or anything like that. It's just trying to more directly elicit information from the model. But nonetheless, they demonstrate that this is useful. And then there's also other methods that actually try to look up information explicitly to answer these questions, which are even more powerful than what we have here. So that's what I'd like to introduce next. And basically the idea here is this is a method that instead of just doing chain of thought, it retrieves relevant sentences when you're doing the chain of thought. So like here, we have the follow-up, are follow-ups needed here? Yes. And then this is the follow-up. But if the model itself doesn't know how old somebody was when they died, then it won't be able to answer this. So what they do in order to make this happen is they do BM25 based retrieval over Wikipedia for each of the chain of thought answers. And then they use the retrieved, I think it's like 10 documents or something like that, multiple retrieved documents to prompt the model to basically follow up with its chain of thought. So this is another variety of things that you can do in order to improve. Cool. Then another one that I'd like to talk about is multilingual chain of thought reasoning. I'm going to be talking more about multilingual things in the multilingual class in a week. But the interesting thing about multilingual chain of thought is we have a design decision, right? Like, do we want to just answer questions in the language that we are asking questions in? Like, so if I ask a question in Japanese, am I going to have it go through the whole chain of thought process in Japanese and then answer my question in Japanese? Or do I want it to somehow go through English because the model has been trained on lots of English and it has it's like a better way to take advantage of its reasoning capabilities. Does anyone have an idea about the answer? Who thinks it's better to do it entirely in the language that the question is asked in? And who thinks it's better to do something in English? Okay. So basically the answer is do it in English. And maybe it might be a little bit dependent on the language, but all of the languages they tested, it's essentially that's the conclusion that they came to. And it's pretty stark in this particular paper. This might change a little bit with more powerful models, but I still would be very surprised if this is not like if this doesn't hold still. So you can see it's like approximately on average 7-point increase in the results. And just to be clear here, we have native chain of thought. So this is doing chain of thought in the language itself. This is doing chain of thought in English, but then answering in the language itself. And this is just like translating everything into English. You can try this out too. Like if you speak another language, you can try to do it myself. When I try it in Japanese, it's very clear that like the model seems more intelligent in English. It just seems like it can do other things, even though like intelligence shouldn't be a function of the language that you're asking a question in, right? Like the model should have the ability to answer questions, but because that's how humans work, right? Our intelligence is kind of separated from our language. How well we can express ourselves is a little bit different. But, yeah.
For the final output of this, was it translated back to the original language and then evaluated?
For translate English, I'm not 100% sure about this. I think it was not. So that might be a confounding factor for this one, but it's not a confounding factor for this one anyway. Yeah. Any other questions? Okay, cool. So this is a pretty interesting result here. And the next kind of series of results are going to be based on that I'm going to talk about are going to be based on the quality of the reasoning chains that the model uses in chain of thought. And this one is a simple heuristic for improving the quality of the reasoning chains. And yeah, one thing I should mention is that the quality of the reasoning chain is definitely connected to the quality of the output. Like that's not necessarily the case, right? It could just say a whole bunch of, false, like, actually, no, maybe I'll skip this one and go and explain this one next. So, yeah, actually, sorry, the explanation ordering for this is a little bit hard, but yeah, I'll explain this one next. So, very quickly, there's two ways that you could be reasoning. One way you could be reasoning is doing an explanation first and then predicting the answer. The other way you could do it is predicting the answer and then then giving the explanation. And in general, if you have a reasonably strong model, any of the modern kind of frontier level models right now, doing the explanation first and then making the prediction is better. And the reason why is because chain of thought works and the model is able to break down the questions into kind of simpler. It's able to break down the answer into like simpler questions for like mathematical reasoning or something like that. And then give you the answer. So like, for example, for Text DaVinci 002, which was state of the art at the time of this writing, you see a 5-point boost from using explanation first and then prediction after that. And in accuracy. But for the weaker models, that was not the case. So if you were using GPT-3 that wasn't trained for chain of thought, or you were using OPT, that was not the case. But nowadays, I think basically all models doing the explanation first and then the prediction is better. So going back, Another thing that people have noticed is like if your explanation is wrong, your prediction also tends to be wrong. So if you make mistakes in intermediate steps of your explanation, it tends to mess up your final prediction. So like one of the interesting ways that people have found to improve the explanation quality is they just observe that if the explanations are longer, they tend to be better. It's kind of interesting, but like if they give you more reasoning steps, this tends to be more accurate. And they actually demonstrate that in this paper where here's a simple reasoning chain, here's a more complex reasoning chain, and you actually see for exactly the same problem, they get about a 15% boost. And these are kind of like naturally occurring reasoning chains. They didn't like train the model to give you longer reasoning chains or anything like that. But amongst the naturally occurring reasoning chains, the longer ones tend to be better. And this fact could be simply used to improve accuracy. And so the way they did this is they just sampled multiple reasoning paths, and then they performed self-consistency over the longer reasoning paths. So if you remember what self-consistency is, it's basically like you do majority voting over the answers for multiple reasoning paths. So they threw out the lower quality ones, and that improved overall accuracy. So yeah, that's a thing that you can do. So yeah, going back to systematic studies of reasoning in LLMs, one of the big results that's actually really important to know about is this sort of chain of thought reasoning is considered to be an emergent ability in large language models. And what we mean by an emergent ability is what the name emergent ability typically refers to is that it is something that increases dramatically as the model size gets up to a certain point. So these actually, I'm really sorry, I cut off the thing on the bottom here. This is like OpenAI does this all the time to not tell you how many parameters they have in their models. I did not do it intentionally here because I think it's actually in here in the paper. But like these ones over here are kind of the like 175 billion parameter models and like the larger models. And what you see is like up until a certain point, you get basically zero accuracy, and then the outputs improve. And so for a while, people were really like confused about this. Like, why does this happen? It feels like magic that you get a really, powerful model and then suddenly it gets better. Like at the very end. But actually, there's a much simpler solution. There's not that much magic to this. And we've known about this for a little while, but this paper from 2023 really like expressed it very clearly. So I highly recommend you take a look at this if you're interested in kind of like the emergent abilities in language models. But basically, the thing about emergent abilities is that they're mostly a matter of how you measure your model's accuracy. And so let's say as your model gets better, it gets gradually better at predicting the like a reasonable next token. So this is like a, I don't know, like 200 million parameter model, 500 million, 1 billion, 3 billion, 7 billion, and like 70 billion or something like that. And so this is like the next token prediction accuracy, or like the accuracy of predicting a reasonable next token that won't result in your reasoning chain being wrong and making a mistake. And so if you have an accuracy like this, in order to get the correct answer, like let's say there's about 5 or 8 places where you could possibly make a mistake in the derivation. Like one common places to make a mistake in a derivation for math, for example, are where you predict a number, like where you predict the result of an equation. And you might have 5 reasoning steps where you might predict the result of an equation. And so if we do this, let's exponentiate all of these by 5. Write Python code to exponentiate these numbers by 5. I'm lazy enough that I just asked ChatGPT to do this for me now. And so if we do this, you go ChatGPT. So now we are getting something that looks like 0, basically 0, 3%, 23%, 9%, and 90%. So what you can see is there's actually a pretty steady gradation of like the next token prediction accuracy here. But if you need to predict multiple tokens correct, then it looks like it's doing basically nothing until you get up to like 75% next token accuracy, and then it starts taking off. So that's like what happens in emergent abilities. And you'll notice that most things that are talking about emergent abilities are usually talking about some sort of chain of thought or some sort of reasoning accuracy. Even if that's not the case, even if they're just predicting a single token, it can still happen because basically the probability of a single token can continue to go up smoothly, but you only get the token correct after the probability starts getting higher than all the others. And that's also a discontinuous function. So basically what this paper shows is like, even if you have like the probability of the correct token going, the correct token going up gradually, you can see this emergent ability based on how you measure it. So that's an important thing to realize about this. Another corollary of this is like, let's say you want to do interesting experiments about reasoning on smaller models. Like, let's say you want to train a smaller model and see how it improves on reasoning. I would definitely encourage you to measure not only accuracy, because you might see like very little change in accuracy, but also measure like log likelihood of reasoning chains or something like that, because you'll see a smoother curve. Cool. Any questions about this? Okay. Sounds good. So I talked a little bit about this. One of the things here that I didn't talk about is this paper measures not just the accuracy of the answer with chain of thought, but it also measures the factuality of the explanation. So basically, whether the explanation is a good explanation for the whether the explanation is a good explanation for the actual derivation, and also the consistency of the answer and the explanation to figure out whether the answer and the explanation match up with each other. And they did this with some synthetic data sets where you could actually measure the reasoning steps by using math. So what they were able to find is basically the answer and the explanation, when the answer and the explanation tended to be consistent, especially for the stronger models. And let's see. Yeah, the answer and the explanation tended to be consistent, especially for the stronger models. And that also meant that if you had higher factuality in the explanation, that translates into higher factuality of the accuracy of the actual prediction. I would bet that these numbers are even higher nowadays. I bet the consistency is even higher with more modern models than Text DaVinci 002. And the reason being is like number one, models are stronger. Number two, all models are like trained for chain of thought pretty aggressively now. So that would make the difference there. Cool. So the other thing I'd like to talk about is training for chain of thought. So there's a fair amount of work in this general direction. From my point of view, there's basically two ways that people do this nowadays. The first way is usually through generating lots of synthetic data that represents chains of thoughts, and then using that to train models. And this is the most famous version of this, although this paper cites a lot of other ones. But basically, they generate a large and diverse chain of thought data set from GPT 3.5 and GPT 4. It includes 5 million complex instructions. I think they generated 1 million from GPT 4 and 4 million from GPT 3.5, just because generating long sequences from GPT 4 is expensive, and they didn't want to do that many. And then they achieve corresponding high accuracy on chain of thought related things compared to other data sets. So compared to like Alpaca, which is much smaller and doesn't have as much chain of thought, and also Vicuna, which is similarly less focused on chain of thought, they were able to do a good job. This paper was by Microsoft, and they didn't actually release the Orca data set for whatever reason, legal or competitive reasons or whatever. But there's another open Orca data set that you can download and use that attempts to replicate it, and it's reasonably good. So you can keep that in mind if you're interested. This is another really interesting paper on trying to create assessments, automatic assessments of how good chains of thought are. And what they do essentially is it's relatively simple. They get human feedback on each step of a derivation. So they just basically ask people, is this step of the derivation good? And if the answer is yes, then they give it a smiley face. If the answer is no, they give it a frowny face. And they use this to train a reward model, where the reward model basically predicts whether each thing of the each step of the derivation is good. And so we have two examples over here. I know this is really small. You might be able to see it either in the paper or on the slides on the website. But what we can see here is that it assesses each of these steps and checks that the answer is good. But it's also able to identify places where like steps are incorrect, and then the final answer becomes incorrect. And then they use this for training a chain of thought style model. So they have the model generate chains of thought, and they assess them with the reward model and upweight answers that have good chains of thought. And so the good thing about this is they actually don't need the correct answers to train the model this way. And because they don't need the correct answers to train the model this way, they can also train the model on lots of other questions. The reason why this works is because, like chain of thought makes it easier to generate each of the steps in the derivation, it's also easier to assess whether an individual step in a derivation is wrong than assess whether the answer is correct overall. So this feedback signal is easier to get model provided than it is for like getting feedback on the answer itself. Yeah.
If failure in one step causes all the other steps to fail,
Yep.
do you just assess the next steps based on the assumption of the previous steps, or do you still like waterfall the failure?
I don't think they do that. I think they it's a good question. I'm not 100% sure about this, but I think they assess each one of the steps independently. And it's not necessarily the case that like failing on this step means this step is wrong, right? It could be just not using it at all also. So. Cool. So a final thing I'd like to talk about, which I think is kind of interesting, is abductive reasoning or learning explanations from data. And sorry. So basically the idea is, can we find a rule that underlies a pattern in data? And here are some examples of this. The basic idea is if we have examples, which are like, if I put a cylinder and a square, a cylinder and a cube on this pink block, I get a noise. If I put just the cylinder on the pink block, I don't get a noise. And you want to discover underlying rules based on the data that you observed. And so why would you want to do this? There's a couple reasons why you would want to do this. The first reason why you would like to do this is because you might want something that you can explain to humans, right? You can explain this underlying pattern exists in this data. It explains why the data, appears as it does appear, and then humans can go in and analyze it or something like that. So recently, there's been a big focus on like using large language models for scientific inquiry and other things like that by coming up with good explanations for why data is the way it is. So if we were able to do that, that would be really interesting. Another thing is language models are not particularly good at coming up with, they're not particularly good at being consistent about difficult tasks across very large, numbers of examples. So if you could look at like all of the data at once, infer general rules from them, put those rules in a prompt, and then apply that prompt to make predictions on new examples, you might be able to raise your overall accuracy as well. So it's kind of like, that's how humans learn as well, right? We don't like just memorize each example. If we just look at a few examples, then we might, not generalize well to new examples. So we kind of try to abstract away general rules. So this is also similar to program induction from input-output examples, which I talked during the code generation class. So you have like input-output examples, and from them, you would like to come up with general rules. But this is a little bit more general. It doesn't necessarily need to be a program that you're inducing. It could be, a grammar, or it could be an explanation, or it could be anything else like this. So there's a bit of work on rule induction with LLMs. It's pretty recent work, but I think it's pretty interesting. So the first one is hypothesis generation, or the first step of this particular work here is hypothesis generation. And basically what it does is it takes all of these, input-output examples, and from these input-output examples, it predicts these rules. Like the answer is always 1, or you want to pick the smallest one, or you want to pick the first element. And then you evaluate it. And so you pick the smallest one, and you can either evaluate it using another language model, or you can evaluate it using using a symbolic evaluator. If it's a program, you could use a symbolic evaluator. If it's a language model, you could just ask the language model to pick, answer 1 always, or pick the smallest one, or pick the first element. And then you get lots of outputs. And then when you get lots of outputs, you then can compare them against the expected outputs and verify whether the rule is correct, verify whether the rule gives you the appropriate answer. And once you've done that, you can go back and do hypothesis refinement, and maybe even give this feedback about like what was wrong, and gradually refine, more accurate and more complex hypotheses. This is another variant of this idea, which uses different methodology. I think both are completely valid, but this one has a little bit higher data constraints. So basically what we do is we use hypotheses in chain of thought reasoning and keep ones that result in correct answers. So this is the step where they're trying to induce rules. And so here this says, in base 9, what is 76 plus 14? And they used base 9 here, obviously, because if it was in base 10, the language model would just solve the problem, and it's not very interesting. So they did base 9 addition. And so the answer is 1 we have, or the answer provided by the language model is we have 6 plus 4 equals 11. The digit is 1 and the carry is 1. We have 7 plus 1 plus 1 equals 10. The digit is 0 and the carry is 1. A leading digit is 1, so the answer is 101. And this verifies, so they get the answer correct. And so they know that they assume that this derivation is also correct. And then they extract particular rules like 6 plus 4 equals 11 and 7 plus 1 plus 1 equals 10. And they add this to the rule library. So then the question is, how do they extract the rules? The way they extract the rules is they have an in-context prompt, which surrounds the rules by basically XML tags that says this is a rule that should be extracted. And so then anything that is in an XML tag, when you get the correct answer, they extract and add that to the rule library. And then conversely, like if the derivation, if the answer is wrong, they just don't add it, or they add it as a negative example and say this is an incorrect rule. And then in the final step where they do deductive reasoning, they can then go ahead and use these rules and improve accuracy. And they demonstrate that that helps. So basically, these are two different approaches. One is extracting directly from the chain of thought. The other is a priori trying to generate rules from the whole rule base, and then verifying them. Notably, both of these require verifiers. And so in some recent work, which I hope will be on archive very soon, we took a look at whether language models themselves can verify their own hypotheses. And so that removes the symbolic verifier here by just asking the language model whether the output is correct or not. And we found that with very powerful language models like GPT-4, you can actually do that as well. So that removes the necessity to have a symbolic verifier in the loop as well. Cool. The reason why I wanted to introduce this is I don't know if like it seems like all of these have been applied so far on kind of very toy examples, like, like, honestly, I don't really care about whether I can play Tetris or, find the largest or smallest number within a, list or something like this. But I think they have like really exciting possibilities for how we could extract more general patterns and like use these to improve language model-based systems. So I think it's a really exciting research direction. Cool. Any questions about this? Yeah.
Yeah, how does the running with the last time can be applied?
Yeah, so that's a good question. So I think tool learning is maybe kind of a subset of this, possibly. Like, I feel like in tool learning, you're learning functions that are, I don't know if they're like good explanations of the data, but at the very least, they're like useful. They're useful rules for solving the task. So I feel like they're approaching it from two different motivations, but actually the methods that they're using are similar. So like, for example, in our tool learning work, Trove, we generated like multiple options for tools, and we kept the ones that had high self-consistency. So that's kind of like the verifier step, right? And then we threw away the ones that weren't useful. So that helps make a concise rule set. So yeah. And then like, could we use tools to attack kind of the more like conceptual reasoning stuff? I don't actually know the answer to that. It's a good question. Yeah. Any other things? Okay. Another final one that I'd like to introduce. This is really like, I really, really like this paper, just from the point of view of its ambition and motivation. And the idea is that they want to learn differences between text collections. And why would you want to do this? There's actually a ton of reasons why you would want to do this, but the best one that they give here is actually, no, sorry, maybe I didn't. Okay, so this is a less interesting one. The more interesting one that they give in the paper is examples of reports from patients who took an actual drug and took a placebo. And so patients write about like their symptoms or how they felt, or they have checkups or things like that are all written in natural language. So one of the things that doctors try to do is they try to look at all of these reports and figure out if there's any like consistent difference between people who took a placebo and people who took an actual drug. And this is like a major part of medical trials, right? And so the idea is like, given all of the texts of people who took the drug, given all the texts of people who took the placebo, could you automatically extract differences between them in some way? And so the methodology that they use for this is they have like group A, the Manchester United soccer squad welcomes rising star as Serena Williams joins the UCLA women's tennis roster, and then you have like 20 more examples. And then here you have Egypt's president at the African Union Summit, and other things like that, and 20 examples not seen here. And so then if I asked a question, the original data set includes news summaries. The two corpora are generated based on when they were published. Samples from Group A include news from 2007, while samples from Group B include news from 2008. I'm a journalist trying to understand what topics are popular across years. Please write a list of hypotheses separated by bullet points of how data points from Group A differ from those of Group B. And then formatting information. And so based on the two sentence groups, A and B from the above, more sentences in Group A mention a sports team or mention about academic relations or things like that. And so what this allows you to do is it allows you to come up with a whole bunch of hypotheses about why one might be better than the other. So the problem with this, though, is like because of language model, limits, number one, they might just hallucinate things and be totally wrong. Number two, the size of the context that they can take into account when making this decision is relatively small. So the next thing that they do is then they have a much larger corpus of text with like 1,000 examples or something like this. And then they treat each of these hypotheses as a classifier. And then they go through all of the examples from corpus 1, which is like maybe 2000, year 2000, and then corpus 2, which is year 2008. And they ask the language model with respect to all of them, does this sentence mention a sports team recruiting a new member? And so you get a classification for each one of these. And you get a certain number of ones and zeros. And so once you have a certain number of ones and zeros, what's the next thing that you would do here? Any ideas? How do you tell if there's like actually a difference between these two? Between two sets of numbers like 1 and 0. A hint is you probably had to do this for assignment 2. Yeah? Yeah, exactly. You do a significance test between the two. And so what you can then do is you have lots of hypotheses, you have lots of significance values. You can order them by the significance value and say the most significance or the difference with the like lowest p-value between them is the one that's most likely to be an actual difference between the two. And you can find the news in 2007 indeed tended to talk about X more than other things. So I actually used this in one of my unrelated projects where I wanted to find the difference between language models, sentences that language models aligned well with human brain signals, and sentences where language models didn't align well with human brain signals. So we we had some data of human brain signals, and we had a measure of alignment on each sentence. And it actually found some pretty interesting hypotheses, like language models tend to align less well with human brain signals on metaphorical language, or a language that had to do with interpersonal relations, or other things like that. And then we actually went in and pursued these to examine them further. And we didn't entirely rely on this, like significance tests, because I didn't quite trust language models that much to like shape my entire research agenda around them. But we came up with other ways to measure it, and some of the things checked out, some of the things didn't check out. So again, I think this general direction of like, how can language models help us answer, complex research questions that we wouldn't be able to easily or very efficiently, that would require normally humans annotating lots of data, is an interesting topic as well. Cool.